Okay, gamma is equal to eta 2 minus eta 1 by eta 2 plus eta 1 we got, and transmission coefficient tau is equal to 2 times of eta 2 by eta 1 plus eta 1 we got. Then we have seen the electromagnetic wave equation when it is traveling in the arbitrary direction. So I told like this, if the wave is propagating in a positive z direction, we have to use omega t minus beta z as the phase. Okay, that means here minus beta z will come. If the wave is traveling in the positive z direction, that is minus beta z. If the wave is traveling in the negative z direction, that is plus beta z. Next, similarly, when the wave is traveling in positive y direction, minus beta y, negative y direction, plus beta y. If the wave is traveling in the positive x direction, minus beta x we have to take. When the wave is traveling in negative x direction, we have to take plus beta x. That means in all these 6 cases here, the electromagnetic wave is traveling along the axis only, either positive or negative axis. Okay, but instead of this one, if the wave is traveling arbitrarily, that means in between the two axes or among the 3 axes, if the wave is traveling, so we cannot able to represent mathematically the electromagnetic wave, either electric field or the magnetic field using this particular way. But if you closely observe these things, so this minus beta z, for example, if I take this beta z, what is this z actually? Z is the distance traveled by the electromagnetic wave in the z direction. How much amount of distance is traveled by the electromagnetic wave in the z direction? That is z is equal to 5 meters to 10 meters like that. So beta z is that phase. Okay, it is a phase available for the electromagnetic wave whenever it is traveled a certain distance in the z direction, that is z is equal to 5 meters. Then this beta is radians per meters into here 5 meters. Okay, it is some radians per meter. For example, it is 2 radians per meter. That is the beta. And z is equal to 5 meters I have taken, so that you will get a 10 radians you will get. So in this way, the phase will be calculated, but it is along the z direction only. So whenever it is traveling in the arbitrary direction, at that time, what we need to do? Beta times here whatever the distance is traveled by the electromagnetic wave in the arbitrary direction, that distance we have to take. That's it.
ఇంటర్నెట్
Okay,
క్లాస్
what?
చెప్తుండే
మాట్లాడకండి అమ్మా. Hello. So here beta times of distance we have to take. So distance traveled by the electromagnetic wave in the arbitrary direction. If it is in the x direction, we have to take beta x. If it is in the y direction, beta y. If it is in the z direction, beta z. Okay, so but if it is in the this arbitrary direction, we cannot represent with x, y, z. So the distance we have to identify. That is the topic we have seen in our previous classes. That is electromagnetic wave in the arbitrary direction. At that time, what we have taken. So if you observe the diagram in the previous diagram, that is the we have represented the distance traveled by the electromagnetic wave with OA. This is x, this is y, this is z. So the distance traveled by the electromagnetic wave we have taken like this. This is the constant phase plane, and A is the point available on the constant phase plane. This is OA. OA is the distance. That's why I have written here beta OA. And that OA we have written in terms of the projections of all the points available on that particular plane. That is given by n cap dot r bar. So this is nothing but OA. Okay, so we came like this. Beta into distance is to be taken. So the distance we have taken OA, that OA can be written in terms of the n cap data r bar. What is n cap? It is about the direction of propagation. Unit vector in the direction of propagation. Unit vector means its magnitude is 1. And n cap we have defined. N cap is equal to this direction of propagation is making certain angles with the x-axis, y-axis, z-axis. It is one vector. So what is its projection on the x-axis we need, what is its projection on the y-axis we need, and what is its projection on the z-axis also we need. And we have calculated them, and we got cos of theta x, cos of theta y, and cos of theta z. So it is n cap. And what is r bar? R bar is like we have taken it is OP bar. P is any other point on this particular constant phase plane. So OP bar itself is R bar. And that is one general point. That general point can be represented with the XX cap plus YY cap plus ZZ cap. So it is one vector, n cap is other vector. So in between these two dot product we can done. So dot product will give the projection. That is the distance exactly. So OA is equal to, it is a not vector, it is just a scalar. It is the dot product between n cap and R bar. And what is that we got? X cos theta x plus y cos theta y. We are multiplying the corresponding projections plus z into cos theta z. So this is the distance. So this one is to be multiplied with beta. Then comfortably we can able to write the electromagnetic equation, either electric field or magnetic field. So if you want to see electric field equation, peak value is E naught. And if it is having the attenuation constant e power minus alpha z and e power j times of omega t minus beta times of OA. Like this, we have to write for the wave which is traveling in the arbitrary direction. So OA is the distance traveled by the wave. And whatever the direction is there, the direction we have to write in the direction we have kept in this particular form. This is the direction of the electromagnetic wave. Okay, so E naught into e power minus alpha z e power j omega t minus beta times OA we are writing as n cap dot r bar. Okay, and then k bar we are defining the new vector we are defining as beta into n cap, so that you can rewrite the e bar expression like this. E bar is equal to E naught into e power minus alpha z e power j times omega t minus k bar dot r bar. So like this we are writing. Okay, so we are going to use this type of expressions in our next classes. Okay, that is why we have to understand this particular thing. So when the wave is propagating in the arbitrary direction, this k bar will come into the picture. That means n cap and r bar, all these things we have taken. So electromagnetic wave representation is different compared to when the wave is traveling along any one particular axis like x, y, z axis. Okay, so this is what we have studied in our previous class. Now, just before going to this exactly oblique incidence, I will extend this particular topic. So, we have understood that the phase gained by the electromagnetic wave by traveling certain distance OA in the arbitrary direction, that is beta OA. So, OA we have written n cap dot r bar. Next, we got like this, that is x cos theta x plus we can take y cos theta y plus z cos theta z. Like this we can write. Okay, n cap dot r cap means we got like this. Okay, or I will write for your convenience. I will write n cap once again. Cos theta x x cap plus cos theta y cap plus cos theta z cap. And what is r bar? R bar is general vector x cap y cap plus z cap. Like this we can write. Okay, then you can see this particular equation in a different manner, like beta times cos theta x into x plus beta times cos theta y into y plus beta times cos theta z into z. Now you treat this is one component, this is another component, this is another component. So that one I'm taking as beta x into x plus beta y into y plus beta z into z. Just we are remodifying the equation. Now it is looking like the dot product of the two vectors. One is x, y, z. Second one is beta x, beta y, beta z. So we can rewrite like this. So beta x, x cap plus beta y, y cap plus beta z, z cap. So like this we can write, it is one vector. It is in dot product with x cap plus y cap plus z cap. So in this manner we can write. So by performing the dot product, x components are to be multiplied. That means beta x into x plus beta y into y plus beta z into z. All the components are to be multiplied, and summation we have to take. So in this manner we are getting. So whatever the equation is there, just we are remodifying that one. It is equal to this one. It is equal to this one. So we have just to remodify like this. Okay. So just to try to remember this one and these things, we'll see about this one in detail in the next class. Okay. For the time being, now we'll start our oblique incidence. So whatever the next two topics we are going to see, these are very somewhat difficult to understand. Okay, but important topics. So listen carefully. Normal incidence means what we have taken. It is the boundary, and in the explanation I have taken xy plane is the boundary. X-axis, whatever the line you are seeing vertically, that is x-axis, and y is coming out of the screen. Okay, then z is normal to the boundary, like this we have taken. Okay, and in this particular topic we have taken the electromagnetic wave is normally incident on the boundary. It is normally incident on the boundary. That means what is the normal actually z? That means in the z direction only the electromagnetic wave has been propagated and striking this particular boundary. And because of the impedance mismatches, eta 1 is not equal to eta 2. So the wave will be reflected back. Certain portion of the wave will be reflected back and certain portion will be transmitted into the second medium. So this is what we have studied in our normal incidence. That means in the normal incidence, how much angle is made by the incident wave with the normal to the boundary. Okay, see carefully. In the normal incidence means in this particular case, what is the angle made by the incident wave? This is the incident wave. Okay, so incident wave is going like this. Incident wave, the question is how much angle made by this incident wave with the normal to the boundary. Normal to the boundary means this one. This is the normal to the boundary. I will change the color. Normal to the boundary is this one. This is the normal to the boundary. So wave is also propagating in parallel with the normal to the boundary. That means it is making the angle is 0. Okay, we are taking this angle of incidence, angle of reflection, angle of transmission, all these things with the normal to the boundary only. Okay, so with respect to normal to the boundary, angle of incidence is equal to 0. Okay, so simply normal incidence can be defined like this. If theta I is equal to 0, that can be taken like normal incidence. If theta I is equal to 0, that is said to be normal incidence. If you don't take theta I is equal to 0, then that is called oblique incidence. That means the incident wave is making certain angle. The incident wave is making certain angle with the normal to the boundary other than 0. So that we can tell that is the oblique incidence. So how the corresponding figure will be there means we have to draw like this. So this is the boundary. Again, I'm taking xy plane is the boundary. So x, y is coming out of the screen. Y is coming out of the screen. And z is normal to the xy plane. So this is like this. Okay. So this is the boundary we have taken. Xy plane is the boundary. Now some new terminology will be coming. So you should be careful to understand that one. Without understanding the terminology, you can't able to understand this particular topic. So XY plane is our boundary. You have to visualize that one. So x-axis is vertical line, y-axis is coming out of the screen, and the boundary is the plane. It is a surface actually. Okay, and z is normal to the boundary. So we can take that is n cap. Because we are studying about the oblique incidence, so the incident angle should make certain angle other than 0 with respect to some non-zero angle it should make with respect to the normal to the boundary. Normal is this dotted line or this horizontal line, whatever I have taken. This z-axis is the normal. Okay. Now this blue color line is indicating the incident wave. Blue color line I am taking as the incident wave. So we can able to observe the angle theta I is available in between normal and incident wave. Okay. Whatever the incident wave is there, this blue color line is making certain angle theta A with the z-axis. Z-axis is our normal. So that is the angle of incidence. So clearly we can tell it is not equal to 0. Now we can tell it is nothing but oblique incidence. Okay. Again, after striking that particular boundary, because of the impedance mismatch, that is eta 1 is not equal to eta 2, this electromagnetic wave after entering into medium 2, it is not maintaining the same angle theta I. Okay, it will be refracted. The refraction nature is possible for the electromagnetic waves. So we have seen about that one in our boundary conditions also. So whenever it is changing its medium, then because of the impedance mismatch, it will be refracted. So angle will be changed. So the angle made by this transmitted wave after entering into medium 2 is making certain angle with the normal to the boundary, that is called angle of transmission theta t. Okay, so theta I is angle of incidence. Theta I is angle of incidence. Theta t is angle of transmission. Okay, and only certain portion of the input signal, that means incident wave, has transmitted into the medium 2, and remaining power should be reflected back because of the impedance mismatch. That means it will enter into the medium 1 only. Okay, this left side part is the medium 1, right side part is medium 2. So this reflected wave is also making certain angle with the normal to the boundary, that is angle of reflection theta r. Angle of reflection theta r. Okay, so we are dealing with three angles here: theta I, theta r, and theta t. So in this manner something is there. So here also we are going to get to what is the reflection coefficient and what is the transmission coefficient. But under this oblique incidence, we are going to study two types. Two topics are there here: oblique incidence. In under this, we will study two topics. One is perpendicular polarization, and the second one is parallel polarization. Perpendicular polarization and parallel polarization. These are the two topics we have under this oblique incidence. So in these two polarizations, the electromagnetic wave is making some non-zero angle with the normal to the interface. So these two are coming under oblique incidence only. But what is meant by perpendicular polarization? What is meant by parallel polarization? That is what we have to see. So in our polarization topic, that polarization was defined with respect to electric field. So the names perpendicular polarization and parallel polarization are also given with respect to electric field only. So with respect to electric field, the names were provided here. Okay, with respect to electric field. Okay, so how the name perpendicular polarization was come and how the name parallel polarization was come, we are going to see now. Okay, so I told that new terminology will come, that is a plane of incidence. Plane of incidence. Already you have understood that the electromagnetic wave is making certain non-zero angle with the normal to the interface. So this plane of incidence means it is related to incident wave. One point is plane of incidence means here incidence is there, so it is related to incident wave, and it is surface. It is plane. That means it is one surface. So what is plane of incidence means the plane which contains the plane which contains incident wave So the incident wave, the plane which contains the incident wave and that means incident wave direction of propagation and this normal to the interface, normal to the boundary otherwise, normal to boundary. So these two are available in one plane that is called plane of incidence. Now can you tell in this particular diagram what is the plane of incidence? Means we have to see this theta I direction is there, the plane which is containing the direction of propagation of the incident wave. That means this line should be available and normal to the interface also should be available. Okay, these two are available in which plane means these two are available on the screen. Normal and direction of propagation of the incident wave. These two are available on the screen. Screen is which plane? Either XY plane or YZ plane or ZX plane. You can answer this one. In this particular diagram,
Exactly.
XZ plane. The screen is the XZ plane. That means plane of incidence is the XZ plane. So this is what you have to understand. So in this particular example, whatever the diagram I have taken, in this case, XZ plane is the plane of incidence. Okay. So this is what you have to remember. Okay. Now, with respect to this plane of incidence, we are going to define perpendicular polarization and parallel polarization. Okay. So I'm going to the next slide. So again, I will draw that particular diagram. So actually, we are looking for plane of incidence. This is x-axis, y-axis is coming out of the screen, and this is z-axis. Z-axis is normal to the boundary, and we have taken incident wave, which is making theta I angle. Reflected wave is making theta R angle, and transmitted wave is making theta T angle with the normal to the boundary. These three are making angles with the normal to the boundary only. Now, plane of incidence means which is containing direction of propagation of the incident wave and normal. So which plane it is containing means XZ plane. XZ plane. Okay. So now we are going to defining this perpendicular polarization and parallel polarization. So carefully you have to listen. Parallel polarization. So in case of the perpendicular polarization, the electric field of the incident wave or all the electric fields of the incident wave, reflected wave, and what is that? Transmitted wave. All these electric fields are perpendicular to plane of incidence. Okay, so here also we are defining these two types of the polarizations with respect to electric field only. So electric field is perpendicular to the plane of incidence. Okay, that means the electric field is perpendicular to XZ plane. In this example, it is XZ plane. So electric field is perpendicular to plane of incidence, then that is called perpendicular polarization. In our example, our plane of incidence is XZ plane. So electric field is perpendicular to XZ plane. What is perpendicular to XZ plane generally? Which is perpendicular to
Why?
XZ plane? Y. That means that here we are going to represent electric field in the Y direction. Okay. Now parallel polarization. Parallel polarization means the just opposite we have to take. Electric field is parallel to the plane of incidence, or electric field is in the plane of incidence. Is in the plane of incidence. That means electric field should be available in the XZ plane. You have to draw this one electric field in the x-z plane only. If you draw like that, then we can tell that is parallel polarization. Okay, so in this manner we can tell. And some other names are also given for the perpendicular polarization and parallel polarization. So at this moment, I'm not touching them. You will be confused. So when you come to the offline classes, at that time I will tell. Okay, this perpendicular polarization can be taken like a horizontal polarization. Okay, horizontal polarization or TE polarization, like there's some other names are there. Why horizontal polarization means that name was given with respect to boundary. These names are given with respect to plane of incidence. Perpendicular polarization and parallel polarization are given with respect to plane of incidence. But horizontal polarization and vertical polarization, these are also names of these polarizations only. These names are given with respect to boundary. Okay, so you can understand this one easily. Electric field is perpendicular to the plane of incidence means that means electric field is perpendicular to xz plane means electric field is parallel to y. Okay, that means electric field is available in the y direction. So if you assume in the diagram, it is parallel to the boundary only. Okay, it is parallel to boundary electric field, so that is called horizontal to the boundary, parallel to boundary. That's why that is called horizontal polarization. Okay, so like that, these names are given. About these different types of the names, we'll see later. First, you concentrate on this particular diagram. Okay, just at least in this particular class, we'll complete the diagram. It's already 12. So now I'm going to draw the diagram. Carefully, you have to listen. Diagram itself is very, very important. Okay, so here I will take two more diagrams. So one is a parallel polarization, second one is a perpendicular polarization. So I'm taking the boundary. Here also I'm taking the boundary, and boundary is a xy plane, xy plane, and normal is z axis in our case, z axis. Okay, so see carefully: incident wave, transmitted wave, reflected wave, incident wave, transmitted wave, reflected wave. I'm going to draw here perpendicular polarization, parallel polarization. To understand these diagrams itself will take a lot of time, but I will complete now. And in the next class, we'll continue that. So perpendicular polarization means how the electric field must be available. You can answer.
Perpendicular to plane of
Plane of incidence. That means perpendicular to x-z plane. That means perpendicular means it should come out of the screen. So electric field should come out of the screen like this. So here we are going to represent E field, H field, direction of propagation. Whatever the blue color lines I have given already, these are direction of propagations. Okay, these are direction of propagations. Now electric field and magnetic field we have to represent. So this is incident wave. What you are seeing like in the third quadrant, that is incident wave. What you are seeing in the first quadrant, that is transmitted wave. Okay, here I will write capital I. This is incident wave. This is transmitted wave. This is a reflected wave. So in all the three waves, the electric field must be perpendicular to the plane of incidence only. That means that should come out of the screen or going into the screen. So we are working with the positive quantities of the electric field. That's why we have taken it is coming out of the screen. So transmitted wave is also exactly coming out of the screen only, so that we can take it is ET. Okay, one vector that is coming out of the screen. Okay, so for the reflected wave also it is going, so it is coming out of the screen, that is ER. So you are not seeing a line for these three. You are seeing the dot circle that we are indicating that that vector is coming out of the screen. And you are observing the this direction of propagation. So two things are over for the three signals: incident wave, reflected wave, transmitted wave. Direction of propagation I have mentioned, electric fields I have mentioned. Now our job is to represent the magnetic field. For this, we are going to use our right hand. Okay, right hand rule we are going to use. So just I will switch on the camera and I will show how to see that particular thing. You have to apply for those three. It is very, very important and you may not understand it in the first level. Okay, I'm stopping this particular screen sharing. So you can observe now. So already in our previous class I have told. So for example, now electric field is upside like this. Magnetic field is in this direction. Okay, electric field is up direction, magnetic field is in this particular direction. Then what we need to do means our fingers, we have to close in such a way that from electric field to magnetic field we have to close. Okay, you see like this. From electric field is upside, magnetic field is towards the screen like this. I'm taking. So when you close your four fingers from this electric field to magnetic field, then this thumb is representing the direction of propagation. In the diagram already I have mentioned electric field and the direction of propagation. So by having these two, we can identify the direction of the magnetic field. So this is what we are going to apply now. We can use fingers also like this. Okay. So electric field is upside by the forefinger. Magnetic field is shown by the middle finger. Thumb is representing the direction of propagation. Okay. But we may not twist our fingers like this in a convenient manner. So we can use like this. If it is in the if you keep your four fingers, you are closing your these four fingers from electric field to magnetic field like this. Okay, electric field is in this direction, magnetic field is in this direction. So if you try to close this, what we can tell, four fingers from the electric field to magnetic field, then this thumb is indicating the direction of propagation. This is what we are going to apply. Okay, so okay, see carefully. Now electric field is coming outside. Okay, so in which direction we have to draw the magnetic field now in order to satisfy the direction of propagation? But I'm concentrating on the incident wave only. Okay, see only incident wave. Electric field is upside. So your right hand four fingers must be coming out of the screen and your thumb should be in the direction of the propagation. That means line we have drawn in that particular direction. Again, I'm repeating, we are talking for the incident wave only. Electric field is coming out of the screen, so your right hand thumb is representing direction of propagation. You keep on your screen. Okay. And your thumb should be in the direction of the propagation. Electric field is coming out of the screen. Then you try to close your fingers. Then in which direction these will be closed means I will draw the this magnetic field. Now you can compare that one properly. So in this direction, you will get the HI. Have you understood this one? How did I draw this HI direction? That means incident wave magnetic field. So now, if you don't get now, you can check. You need to close your fingers, right hand four fingers from electric field. Electric field is coming outside. From electric field to magnetic field, if you close like this, your thumb is representing in the direction of propagation. Is it okay? Did you understand this one? How did I draw this HI direction?
Yes, sir.
Okay, then you no need to bother about the transmitted wave. Okay, how you have written this incident wave magnetic field in all the cases, whatever we are going to study, this magnetic field incident wave will be coming in the same manner. So HT will come like this. But you need to work again for this reflected wave because the direction is reversed here. Okay, so you can try that one. I will draw. You can check that one. This electric field of the reflected wave is coming outside. Okay, then you need to represent this thumb in the direction of propagation. So you have to just rotate your hand and you need to follow the rules as it is. So your thumb, first you keep your right hand thumb. First you keep your right hand thumb in the direction of the propagation of the reflected wave. Then you see how your four fingers are moving. from the electric field to magnetic field. That means it will come like this. Did you get like this only? Have you understood this one? HR. First, you keep your thumb in the direction of propagation, then you will get clarity. Is it okay? Hello? Hello? Anyone can respond. Is it okay for you? Did you understand?
Yes, sir.
Yes, sir.
Okay. Okay. Have you understood all these
Yes, sir.
directions, whatever I have drawn?
Yes,
Okay.
sir.
Then same thing we have to do for the parallel polarization. But parallel polarization means electric field must be in the plane of incidence. That means how we have data representations with green color for the magnetic field in the perpendicular polarization. Here, the vectors for the electric field will be represented on the screen now. Okay, so electric fields are available in the plane of incidence. Magnetic field will be perpendicular to the plane of incidence. You try for this one in the next class. We'll see. That means in the offline classes only. Okay, you don't skip this particular topic today. If you learn, time will be saved. Okay, only 1 week will be there na, at that time. So we have to see the derivations part. Derivation part is somewhat lengthy here. Understanding the derivation also will take a lot of time. It is just about the diagram only I have told. For the diagram itself, it has taken this much amount of time. Okay, same thing we have to repeat for the parallel polarization derivation part also somewhat difficult to understand. So here we need to get the reflection coefficient and the transmission coefficient in the both the cases. Okay, for the perpendicular polarization and for the parallel polarization. Okay, very interesting topic that we are going to see. Okay, so with this I'm closing. If you have any doubt, you can ask me. Hello. Please respond. If you have any doubt, you can ask. Otherwise, we'll close the session.
Sir, in parallel polarization, this only the X component is in the plane of incidence, right?
Plane of incidence. That means how we have done. For example, I will draw for the incident wave. You see here, uh, HI should be coming out of the screen. Okay, HI should come out of the screen. Then how to draw this electric field means you can apply this one. First you try to keep your right hand thumb in the direction of propagation. E to H we should come. E to H, not from H to E. Okay, E to H we should come such that we have to draw the electric field. Already magnetic field is there, which is coming outside. Okay, out of the screen. And your thumb is representing a direction of propagation. So how, in which direction this particular E must be available? E should be available in this particular direction. Did you understand this one? E to H, if you move like this, then your thumb is indicating in the direction of propagation. So it is true. And already I told about the incident wave. You can draw for the transmitted wave in the same manner, but here some twist you will get in the reflected wave. Okay, that we will see in the next class, or you can try that. Okay, any other doubt?
No, sir.
Okay, I'm closing the session.